Hi, I'm Jaden Barnes, and this is...
Noah Fleury,
And we are...
here to teach you about wavelength.
A wave is any disturbance that transmits energy through matter or empty space.
A medium is any substance through which a wave can travel, such as air, water, or even space.
Transverse waves is a wave in which the particles of a medium move perpendicular to the direction the wave is traveling.
This is an example of a transverse wave. Me and my buddy Jaden over here, we're going to show you a real-life example of a transverse wave with the shoelace.
Here we go. That right there are waves, or they're supposed to be. But we have a drawing right here that we drew.
Which represents a transverse wave. So, crests are at the top, and troughs are at the bottom. A wavelength can be either determined from one crest to another crest, or one trough to another trough.
Right.
Now Jaden's going to tell you about amplitude.
Amplitude is the distance between the crest and the middle of the wave. Same with trough. Trough to the middle of the wave is the distance of the amplitude, in which we draw a red dotted line in between to show you.
That's it with transverse waves. We'll see you again.
Now we will be talking about longitudinal waves. A longitudinal wave is a wave in which the particles of a medium vibrate parallel to the direction of wave motion compressions.
A sound wave is an example of a longitudinal wave.
Thanks, Noah. And this is an example of a longitudinal wave that we drew. Actually, I drew. To measure it, you would measure it from rarefaction to rarefaction or compression to compression. Either one would work, it doesn't matter. But rarefactions are always the ones that are usually farther apart, and compressions are usually like really tightly packed. And yep, that's about it for longitudinal waves.
Wavelength vocabulary, part 1. Surface wave, a combination of both transverse and longitudinal waves. An example of a surface wave is an ocean wave. So, flow into you, Jaden.
Thank you, Noah. Next we have amplitude. Amplitude is the maximum distance that the particles of a wave's medium vibrate from their rest position.
Wavelength, the distance from any point on a wave to an identical point on the next wave, such as trough to trough or crest to crest.
Next up is frequency, the number of waves produced in a given amount of time.
Next we have wave speed, the speed at which a wave travels through a medium, such as the speed of light. So, over and out, we're done with vocab part 1. Back on wavelength, with common equations that you use with wavelength. Wave speed is represented by nu, looks like a fancy V. Wavelength is represented by lambda, which looks like an upside down Y. Frequency is represented by a fancy F over there. Over to you, Jaden.
To find wave speed, the formula is lambda times frequency. To find wavelength, the formula is nu over frequency. To find frequency, the formula is nu over lambda. When frequency increases, wavelength decreases.
And vice versa. Wavelength vocabulary, part 2.
Our next vocab word is reflection, which is the bouncing back of a ray of light, sound, or heat when the ray hits a surface that doesn't go through. An example of this would be like looking into a river or a pond and seeing yourself in the reflection of the water. Next is refraction, the bending of a wave as the wave passes between two substances in which the speed of the wave differs.
I'm not grasping this concept, Jaden. Can you show me an example?
Sure, Noah.
Thank you.
See, Noah, right here, as you can see, the laser from what you're holding, as soon as it hits the surface of the water, it bends, coming out through the bottom right here.
Ah, thanks, Jaden. I get it now.
And that's what refraction is.
Our next word is diffraction, a change in direction of a wave when the wave finds an obstacle or an edge, such as an opening.
The amount of diffraction of a wave depends on its wavelength and the size of the barrier or opening the wave encounters.
An example of diffraction is when the light of the room hits the CD, it makes these colors around the CD. That's an example of diffraction. Hey, we're back, and now we're learning about interference. Interference is the combination of two or more waves that results in a single wave. Constructive interference happens when the crest of one wave overlaps the crest of another wave, or waves, to create a larger amplitude.
Here we have an example of constructive interference. When two waves approach each other, they eventually overlap and make the amplitude larger. Once that happens, the waves just keep moving past each other in opposite directions, and that's called wave continuing. I guess she's maybe looking in. I don't know why she does that.
Destructive interference. Destructive interference is when two waves with the same amplitude combine and cancel each other out. Jaden, can you give us an example?
An example of destructive interference would be right here when two waves approach each other, eventually they would overlap and cancel each other out by causing a straight line. They would keep continuing and passing each other going in opposite directions, called wave continuing. And those are examples for destructive interference. Here we have a standing wave, which is a pattern of vibration that stimulates a wave that is standing still.
An example of a standing wave is a deconstructive wave, with a portion where both waves cancel each other out and become a straight line.
A resonance is a phenomenon that occurs when two objects naturally vibrate at the same frequency. The sound produced by one object causes the other object to vibrate. Alright. Thanks for watching our video. If you'd like to give us a thumbs up. If you have any questions, just comment below.
Please subscribe to No Jaden's McFlurry Barnes. Thank you. Bye.